Hey everyone, in this AP Chem series video, we'll take a look at the ion concentrations that form when your solution has an ionic solute. First, remember that for solution concentration in AP Chemistry, the only one we have to know about is molarity, moles of solute divided by liters of solution. In this video, we'll take a look at some special considerations related to molarity that you'll have to pay attention to when your solute is an ionic solid that dissolves and splits into two different types of ions. So the issue with ion concentrations is that when an ionic solid dissolves, it actually produces two different types of particles, the cation and the anion, each with their own separate concentrations. Imagine a beaker of water where we dissolve 0.2 moles of an ionic solid like magnesium bromide. We could take those moles and calculate the molarity of magnesium bromide in the solution pretty easily. 0.2 moles divided by the 0.075 liters, we've got a 2.7 molar magnesium bromide solution. And that number is a pretty good way to describe the solution concentration, but it's also not super accurate because technically, when ionic substances like MgBr2 dissolve, there really isn't even any MgBr2 left because of the way it splits apart as the solution forms. Technically, the MgBr2 solid that once existed has been fully converted into Mg+2 and Br- ions. On top of that, we have some coefficients to pay attention to. Every time a formula unit of MgBr2 dissolves, it produces one Mg+2 cation and two bromide anions. Since there's a 1-to-1 ratio between magnesium bromide and the magnesium cation that's produced, there's also going to be 0.2 moles of Mg+2 in the solution, meaning the magnesium cation's concentration is also 2.7 m. It's a little bit different for the bromide though, because every time that MgBr2 splits apart, you get twice as many bromide cations being produced. That means there isn't 0.2 moles of those, there's actually twice as many, 0.4 moles. That makes the molarity of the Br- 5.3 m, or twice as much as the others. So we have three different molarities, all of which describe the concentration of this ionic solution. Make sure to take some time and write these ideas down. It's also common on the AP Chemistry exam to have to model ionic solutions, and it's important to represent the relative quantities between the two ions. That means if I choose to include two magnesium cations in my model, I have to then show twice as many bromides to represent the 1-to-2 ratio. In this case, that means I'd have to show 4 Br- particles. This would be an accurate way to model the different ion concentrations in my magnesium bromide solution. Make sure to take some time and write that down. Let's close the video with an example. How many grams of sodium phosphate are needed to produce a 300 milliliter solution with a sodium ion concentration of 0.0063 m? Remember to pause the video and try this yourself before you watch me go over the answers. So the first thing I need to do is think about my sodium phosphate and how it dissolves, in particular how many of each ion it produces when it dissolves. Its formula is Na3PO4. So when it dissolves and splits apart into Na+ and PO4- 3 ions, it's going to be producing for every one formula unit of Na3PO4 3 times as many Na+ and an equal amount of PO4- 3s. This is important because if I want the sodium ion concentration in the final solution to be 0.0063 m, that means the sodium phosphate concentration is only going to be 1/3 that amount. That concentration is 0.0021 m. That's the concentration I'm interested in, since sodium phosphate is the chemical I'm adding to the water to produce the solution. Finally, I can start using my molarity formula and plugging in what I know. The final concentration of sodium phosphate in the solution is going to be 0.0021 m. The volume of the solution is going to be 0.3 liters, so I need to solve for how many moles of sodium phosphate are needed to produce this. Solving for moles tells me that I need 0.00063 moles of sodium phosphate added to my solution. I've got one final step. Since the problem asks for grams of sodium phosphate, I've got to take those moles and use the molar mass to convert these moles back into grams. With a molar mass of 163.9 grams per mole, I get a final answer of 0.103 grams of sodium phosphate. That also concludes this video on ion concentrations. Thanks a lot for watching.